So to determine how high an R value is good enough, we do have a hypothesis test that we're going to conduct. Surprise, surprise, what's new? So this is a little different. We only have to consider one hypothesis here. So when you're writing down your two hypotheses for this, it's very simple. It's always the same because we only consider one option. So we have our null hypothesis, which says that there is no correlation between the X and Y variables of the population. So that is that rho is just 0. So there's no correlation. And then our alternative hypothesis is that rho is not 0, which means that there is a significant correlation between the X and Y variables. So if we're ever doing hypothesis testing with correlation coefficients, it's one hypothesis, it's always the same. It's rho is 0, rho is not 0. So that at least makes it easy. So then we have some assumptions like we always do. So one of the things is that the data are quantitative, so they're numerical, and they're obtained from a random sample. The scatter plot shows that the data are approximately linearly related. So if you have a scatter plot and they don't look at all linearly related, what's the point of doing this? So that's one of our assumptions. There's no outliers. So I know when we first introduced this, we talked about how outliers can really affect your scatter plot and your correlation. And then lastly, the variables X and Y must come from a normally distributed population. Pretty standard assumptions. Like I said, I'm not going to give you a problem that doesn't satisfy these assumptions, so don't worry about memorizing them, but they're just here so you can read them. Okay, so then we have a formula because to do this hypothesis test, we're going to conduct a t-test. So our formula is t equals r times the square root of n minus 2 over 1 minus r squared. So r is that correlation coefficient that we found, and then n is going to be the number of data pairs. And then it says the degrees of freedom are n minus 2, where n is the number of ordered pairs. So a little different here. We usually have degrees of freedom being n minus 1. This one is n minus 2. Okay, so that is your formula. Really, when it comes to hypothesis testing, it's all the same process. It's, are you doing the p-value method? Are you doing traditional? They're the same steps. It just depends on what type of test you're doing. So is it a t-test? Cool. What is the formula for the test value? And then everything looks the same. So let's just do an example. So let's do this with the one that we've been working with, which is height and hand span. We've already calculated R last class period, so that makes this a little easier. But let's just state our hypotheses, and I did mean to put here, I did mean to say that I want to use the traditional method to do this example. And I forgot to change the notes, so scratch determining the p-value, because I'm just going to do the traditional method, not the p-value. Okay, so let's state the hypotheses here. So like I said, when you're doing the hypothesis testing with the correlation coefficient, it's very standard, and it's always your null is rho is equal to 0, and your alternative is rho is not equal to 0. All right. And then step 2 is to find the critical values from the appropriate table. So we're using the traditional method, which means that we find the critical regions. I think there's still some confusion on the difference between the traditional method and the p-value method. So maybe that's something that we go over in the review, or if you're still stuck on it, come ask me, because that's one thing that I noticed when grading the exams was that I think some of you had them switched, or maybe you just didn't fully understand what steps were in each of them. I'm not sure. So maybe that's something we can go over in the review, because I get it, there's a lot with hypothesis testing. So I don't want you to miss any points on the final because I said use the traditional method and you accidentally did p-value. So we'll make sure we know that before the final exam. But we're doing the traditional method, so we have to find the critical values first. So to do that, we just need to know what alpha is. And then we also need to know the degrees of freedom. So this is a t-test. So whenever you're doing a t-test, you need to know the degrees of freedom and the significance level, and then you can find the critical values. So you need two things to find the critical values when it's a t-test. So the degrees of freedom, it is the number of data pairs minus 2. So if we come back up to our chart, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 pairs of data. So that means our degrees of freedom is 8 minus 2, which is 6. Okay, and just to give like a recap on how we find the critical values, I'll go through using the table again. So doing a t-test, that means we use the t-distribution. So I'm going to open up that chart. Okay, so this is a two-tailed test. So I guess I lied. I guess you need to know the significance level, the degrees of freedom, and you need to realize if it's a one or two-tailed test. So those are your 3 things that you really need to know. So because our alternative hypothesis is just that it's not equal to 0, so we don't have anything being like less than or greater than, it's just rho is equal to 0 or rho is not equal to 0, that's going to be a two-tailed test. So when you're doing the test for correlation coefficient, it's going to be two-tailed because the hypotheses are always the same. So if we look at our chart, we have a two-tailed test where the significance level is 0.05. So that puts me right there. And then my degrees of freedom are 6. So I just have to look where these intersect. And I get that my critical values are positive and negative 2.447. All right. Okay, so I get plus and minus 2.447. I'm going to go ahead and draw our little like normal distribution like I usually do. That way I can shade in the critical region and the non-critical region. You definitely need to know how to do this for the final because I will ask you to do it. I'll just guarantee I'll ask you to do it. So drawing my distribution here, I know that my critical regions are here, where this is negative 2.447, and here, where this is positive 2.447. And remember, the point of doing this is that the traditional method of hypothesis testing says if you compute your test value and it falls in either of the critical regions, then we get to reject the null hypothesis. So that is the point of drawing this out and looking at it, is that we can visualize what regions allow me to reject the null and what regions don't. So that's why I draw this out every time. Okay, so let's compute the test value now. So I wrote that formula down, and it is t equals r times the square root of n minus 2 over 1 minus r squared. So we found our last class period, and we said it was, sorry, let me go back and check, 0.753. So we have that r is equal to 0.753. And then we know that our number of data pairs, we had 8 of them. So all you have to do is plug these 2 items in. And so you get 0.753 times the square root of 8 minus 2 over 1 minus 0.753 squared. All right, let me plug this into my calculator. All right, and I get 2.803. All right, that is my test value. Something else I noticed on the exam was I think there's slightly some confusion on like the vocabulary. and between like the difference between what a critical value is versus what a test value is. So that's definitely something we can go over too. And I would totally recommend you like know the vocab words really well, because like maybe you know how to do the whole process, but you don't know which one's the critical value and which one's the test value. Like that'll cost you points because you'll do it in the wrong order or something will be mixed up. So I definitely recommend you know like your statistical language, I guess. Okay, so I found the test value to be 2.803. So because we're doing the traditional method, I want to see if this lies within my critical regions. So my critical region is anything greater than 2.447 or anything less than negative 2.447. So why don't we send a private chat, or I mean, you can make it public, I don't care. Do we think we're going to reject the null or not? If you're looking for like a good way to do this, like if this is like still like not something that you're super comfortable with, I would recommend like once you take your test value, try and plot it on the thing that you've already drawn. So draw the normal distribution, shade the critical region, and then plot where the test value falls, because that is like a flawless method for doing this. So 2.803 definitely falls within this region here. It's probably like somewhere right here. So then that's easy to look at that once you've plotted it and then say, oh, that is in my critical region. But sometimes it's kind of confusing in your head to say like, oh, is this greater or less than that? I don't know. So if you're looking for like a foolproof way to do it, plot the critical regions and then just plot the test value with it. Because then that's a very clear and cut, like, is it in the critical region or is it not? So there's a good method. So yes, it's in the critical region, which means that we do get to reject the null. Okay, so now we get to summarize our results here. So the summary isn't too bad. Because we got to reject the null said that rho was 0, and that is our correlation coefficient. So remember, if it's 0, it means there's no relationship. But because we get to reject the null, so we're rejecting the fact that the correlation coefficient is 0, and we get to accept the fact that it's not 0, that means that we get to say there is a significant relationship. So there is a significant relationship between height and handspan. And there we go. That is a nice way to be able to look at this and say, is there a relationship or not? And to not have to like ask yourself, is my correlation coefficient high enough? Or like, how do I decide? How do I just look at a plot and say, is this like a strong linear relationship or not? So this is a direct way to answer that question. Any questions on this process of doing the hypothesis testing? Okay. There's a note at the bottom here that says that you can use the stat function on your calculator with the linear regression t-test little thing to conduct the hypothesis test for correlation coefficient. It does tell you where you can find the directions in your textbook for it. I'm not going to go over it in class, but you can find these directions in the textbook, and it basically just walks you through a tutorial of what buttons to press, like kind of just how I show you how to do it. So if you're curious, that is in the textbook. I am always okay with you using your calculator to check your answer, unless it's one of those weird things like when we talked about how the calculator computes like the degrees of freedom weird if you have like two proportions. So if like we've done it in class or if I've mentioned it, I'm always okay with you checking your work with it. But it becomes a problem when like you don't show any work and then just put an answer down and then it's wrong because I can't give you any partial credit if there's no work. So I recommend doing the work and then maybe just checking it with the calculator. Because at least if you got a wrong answer because of like you entered a number wrong in your calculator, at least if you have work down, I can give you a bunch of partial credit. Okay, last page of this section. So this is probably something that you've heard, maybe not, but I feel like this is a pretty commonly said thing. So correlation does not imply causation. So that means that just because two things are correlated doesn't mean that one necessarily causes the other to happen. So like it says, a correlation between X and Y means that there's a linear trend that exists between the two variables, but it does not mean that X causes Y. It doesn't mean that whatever your X is causes something to happen with Y. So this is a really odd example, but example, as the number of churches increases, so does the crime rate. Really interesting. I don't know, maybe the church-going people are just, they love to commit crime. But that sounds possibly unlikely. Not sure, but this is what's called something like a lurking variable. So it's a variable that influences the association between two variables. So it's something that's present that's maybe causing these to be correlated, but it doesn't mean that one causes the other. So maybe we say, oh, the number of churches increasing doesn't cause the crime rate to increase, but it's more like, oh, maybe the population is increasing and both of them are increasing at the same time. Maybe it does, maybe it doesn't. It's just kind of a funny example. Um, oh, perfect. Yeah. So just saw a chat. Yes, population is totally the one that I was thinking of with this example is that maybe your population as a whole is just increasing. So that means both of them are increasing. So yeah, that's kind of an example that you'll hear a lot. So correlation doesn't mean that one causes the other, just means they happen to follow like the same trend, kind of. So, like I said, that's a lurking variable when something causes an association between two things. So in this example, we could just say an increase in the population. So, so just be very careful when you're talking about correlations between two things that you don't imply that one would cause the other. Okay, that is everything for this section 10.1. Are there any questions about the correlation coefficient or anything that we talked about here?
So if we're going to be asked to do it on an exam or anything, I assume we're going to be allowed to use a calculator. We don't have to remember that formula from Tuesday.
Oh,
Or,
yeah, for sure.
yeah, awesome. That's all. Just wanted to double check.
Yeah. Yeah, you could totally use a calculator. I'm never going to ask you to do that formula by hand. And if it's something where like, if it's something that you can only like really use a calculator for, so something like the formula in the like the notes that I'm just going to scroll back up. Okay, if it's something like this and I ask you to calculate R, I will try my hardest to explicitly state use your calculator or something, because something like this, obviously I don't need to see work for because I don't know what work you would even show for this. So if it's something where like, okay, there's no work needed, you just need to use a calculator, I'll try and say in the problem instructions, like just use your calculator. That way it's like very great. Okay, so we can go on to the very last section. So, woo. Let me open it. All right, so the last section is 11.1. So I've uploaded so I put the lecture notes on Canvas, and then I also put another PDF file of a new distribution. So for section 11.1, we now have another distribution that we're looking at. So we've done the Z distribution, T distribution, and now we have a third one. So this table looks like this. It's in your book. So if you have the book, you can access it, but I just put it up there in case anyone wants to just pull up the PDF of it. So this is what I'll be using for today. Okay, so first thing that I'm going to say is how to pronounce this. This is called a chi-square test. Not a chai, not a chi, it's chi. So this is chi-square. Chapter 11 is all on the chi-square distribution, but section 1 talks about specifically using it for something that's called a test for goodness of fit. So first of all, it says that a chi-square statistic can be used to test a distribution for goodness of fit, so to see if a variable is normally distributed, as well as to test the independence of two variables. So it has a few other uses, but we are just going to look at one thing specifically that it does. So in this section, we're just focusing on testing for the goodness of fit. So what does that mean for what we're doing? It means that we are testing to see if a frequency distribution fits a specific pattern. Might sound kind of weird, but I think an example will really show what we're talking about. So right away, I will just define an example and we'll kind of work with this one example through the whole thing. But before we do that, we will talk about some characteristics here because you've never heard of the chi-square distribution before. So I'll just list 4 things about it. So the chi-square distribution is a family of curves based on degrees of freedom. So that might ring a bell. The T distribution was also a family of curves. Then we talked about degrees of freedom. The chi-square distributions are positively skewed. So that's kind of interesting because before we've just talked about the normal distribution, but with this one, it is positively skewed. And I will draw a little graph at some point. All chi-square distributions are greater than or equal to 0. So we're not talking about any negative values here. And then 4, the total area under each chi-square distribution is equal to 0, or equal to 1. So that is similar to when we've talked about the normal distribution and all that stuff. So the area under the curve is still equal to 1, but a few differences here. So they're all greater than or equal to 0. So now instead of having a normal distribution that's symmetric across 0, so we have positive and negative values on both sides, we only deal with things that are positive. So it literally only lies on the positive side of the x-axis. It's also positively skewed. Okay, so next, the chi-square goodness of fit test is used to test the claim that an observed frequency distribution fits some given expected frequency distribution. Sounds like a lot of words, so let's just talk about an example here. So suppose you wanted to see if there was a difference in the number of arrests in a certain city for the 4 types of crimes. A random sample of 160 arrests showed the following distribution. Okay, so we have a city and we have this random sample here of 160 arrests, and this is what was observed. So this is what we observed from the sample, and then we categorized them. So 38 of them were for theft, 50 of them were property crimes, 28 was drug use, and 44 was driving under the influence. Okay. So it says below, since the frequencies from each type of crime were obtained from a sample, these frequencies are called the observed frequencies. So if you're ever given a problem like this, and it tells you that there was a sample taken and this was the frequency of each thing that occurred, or maybe it's not even an event, but something else, but it gives you the frequencies of things from a sample. That's what's called the observed frequencies. Okay, and then we get into the other type of frequency, which in this case is going to be called expected frequency. So think of the expected frequency as what you would expect to happen, and the observed frequency as what actually happened. So I'll explain a little more. So the frequencies obtained by calculation, as if there was no preference, are called the expected frequencies. So maybe this rings a bell. It's when we talked about things like expected value. And we said, this is kind of what we would expect to happen, but like, obviously that might not be what actually happens. Kind of the same concept here with like, maybe we have expected frequencies, like we expect, I don't know, 40 of each of these. So we expected 40 thefts, 40 property crimes, 40 cases of drug use, and 40 cases of driving under the influence, but this is what we actually got in our sample. So below it tells you how you're going to calculate expected frequencies. So we have two types of expected frequency, which I just named one of them off. So if all expected frequencies are equal, the expected frequency E can be calculated by using E equals N over K, where N is the total number of observations and K is the number of categories. So I'm going to briefly explain what this means and I'll come back to it. So let's look at our example above and talk about the possible expected frequency here if we used this method. So if we wanted to calculate the expected frequency where all of them are equal, so we say, hey, we have the same expected frequency for each category. All we need to do is take the total number of observations and divide it by the total number of categories. So our total number of observations was 160. And if we divided that by the 4 categories, that means that we would expect each of them to have a frequency of 40. That's just like a very like straight across the board, hey, we have 160 observations, just divide them equally upon the 4 categories. That's one method of having like an expected frequency. There's another method. This one might seem more appropriate and more accurate possibly, but it says if all expected frequencies are not equal, then the expected frequency can be calculated using E equals N times P, where N is the total number of observations and P is the probability for that category. So let me kind of explain what this would look like. And we will be doing examples with both types, but I'll just kind of verbally talk about it. So if we wanted to calculate the expected frequencies, and let's say we were given additional information like, oh, the chance of a theft occurring is like 30%. If we wanted to calculate the expected frequency for theft, we would take the total number of arrests and take 30% of that, and that would be your expected frequency. So something along those lines. So if you know the probability of something happening and the total number of like events or your sample, the size of that, you just multiply the probability by the sample size, and that gives you your expected frequency. That should kind of ring a bell with talking about expected value, because that was something that we did, but if it doesn't, that's okay. Basically, all you need to take away from this is that there are 2 methods to calculating the expected frequency. One is where they're all the same, and you just take the total number of like observations or your sample size and divide it by the categories. The other is where you have a little more information, like the probability of each of these things happening, and you can calculate, like, I guess, more specific expected frequencies. Like I said, we'll do a problem with each. And yeah, I would always tell you which one to do in like an exam situation. So I would always say either assume they're all equal and use that method, or use like these probabilities that I've given you to do it. Okay, so those are your 2 methods for doing that. So then it says, assuming there are no differences in the number of arrests for each category, let's do the expected observations. So let's actually calculate them out. So key wording in this sentence here, it says, assuming there are no differences in the number of arrests. So that means that we are going to use method 1 here, which means that we have all expected frequencies are equal, because we're assuming that there's no difference in the numbers for each. So assuming there's no differences, it wants us to calculate the expected observations for each. So if we look at how to do this, it tells us that E is equal to N over K in this situation. So E is equal to N over K. Well, it told me up above that my sample size was 160. So this is equal to 160 divided by the number of categories. So I had 4 different categories of arrests. So if I do this, I get 40. And now I can fill in the last row of my table and I can just say, okay, I expect all of them to have a frequency of 40. So I just calculated the expected frequency. This is what I thought they were going to be, but when I actually had a sample, the top row is the observed frequency, and that's what I actually observed or recorded. Okay. Any questions just on that concept before I keep going? So the reason that we're doing this is because we're actually going to use what I named off as that chi-squared test to see how well that expected frequency that I calculated, so the expected like frequency distribution, how well that actually fits what I observed. So that's why it's called a goodness of fit test. So I'm seeing, did my expected frequency actually fit reality well or no? That's a little preview to why we're even talking about this. Okay, so let's keep going. So the observed frequencies will almost always differ from the expected frequencies due to sampling error. They're always going to be different usually when you calculate them versus what was actually observed. But what we're asking is, are these differences significant or are they just due to chance? So is the difference between my expectation and what I observed, is that actually significant and that means something and there's a difference? Or was there just a difference by chance maybe? Like maybe for that sample there was a difference, but maybe for another sample there wasn't. Was it by chance, or am I usually going to find there's a significant difference? So the chi-square goodness of fit test will enable the researcher to determine the answer to this. So what's nice is, like what we just did before with the correlation coefficient, the chi-square goodness of fit test only has two possible hypotheses again, which is really nice because that makes it nice to write your hypotheses out. So the general hypotheses for the chi-square test are as follows, where the null is that there is no difference in the frequency distribution for each category. So that means that what we put down as the expected frequency was actually a good fit. So that means there is no difference between the actual or observed frequency and what we put down as the expected. So the null says that's true. The null says that my estimation or my expectation is a good fit. And then we have the alternative, which is there is a difference in the frequency distribution, which says that it's not a good fit. So it says that my expected one doesn't really line up with my observed one, and it's not a good fit. There's a significant difference between these two distributions. Obviously, for writing these out, you will have to write them out like with the details given for each question. So like you could get more specific than just there is no difference in the frequency distribution for each category. So you'll see what I mean, but it'll be a little more specific, but it'll follow these general guidelines. All right, so per usual, now we have another formula. This is the formula for your test value. So let me go ahead and write it down. And we write this down as like kind of a squiggly X. So this is your chi-square here. And this is equal to the sum of O minus E squared over E. So the O is going to be the observed frequency, and the E is the expected frequency. So what you do is for each category, you take and subtract what you expected from the observed one, square it, and divide by the expected frequency, and then you sum them all up. And yes, you can do this by hand. I will never give you something that has like 10 categories. I'll probably keep it to like 4. So yes, we'll do this one by hand. And then a little note that degrees of freedom are equal to the number of categories minus 1. All right, so there are some assumptions like usual. Like I said, though, I'm not going to give you anything that doesn't meet these assumptions. So the first one being the data are obtained from a random sample. You'll always see me say in the question, oh, this random sample gives you this. So you're good. Two, the expected frequency for each category must be 5 or more. This just has to do with the computations and what you calculate, but I'm never going to give you something that doesn't satisfy this. If you want to read more about why you need number 2, they do talk about it a little in the textbook, but I won't go into it. Okay, so there is a note here. So it's just a few observations. So by looking at the formula that I just wrote out, where you have that chi-squared is equal to the sum of O minus E squared over E, we can observe a few things. So first being that if there is perfect agreement between your observed and expected value, that chi-squared will always equal 0. And that's because if your observed always matches your expected, O minus E is 0 for every category. So if your thing has perfect agreement, this will be 0. I'm not going to give you a situation where that's true though, but just an observation. Something else is that the chi-squared can never be negative. And that's because we have in the numerator of that fraction O minus E squared. And so that ensures that the difference right there when we square it will always be positive. If you just had O minus E, it could be negative. Let's say E was greater than O, then you could have a negative in the numerator. But to ensure that it's not negative, we just square it. And that kind of lines up with what we think, because we talked about how chi-squared is always positive. So it would be nice if our value that we got was positive. So that explains the square in the numerator. Lastly, the test is always right-tailed because when you have your null hypothesis of a good fit and then your alternative of not a good fit, chi-squared will be small in the null hypothesis case and large in the alternative hypothesis case. So let's say you do have a good fit. That means that expected and observed values should be kind of close. That means that your chi-squared term should be smaller. If you have a bad fit and your expected values and observed values are not really close at all, the chi-squared term will be bigger. So it's always right-tailed, just so you know. And when I draw the little distribution, you'll see that. Okay, so our next set of instructions here is on finding critical values for this distribution. So thank goodness, this is very similar to everything else that we've done. So the chi-square distribution table is in table G, like I said, it's in the textbook, but I put that PDF on Canvas. So table G is set up to give the area to the right of the critical value. So that's nice because when we've done stuff in the past, it's always given the area to the left of the critical value. But this one gives you the area to the right of it, so that's nice. And since all of our tests are going to be right-tailed, we only need to look at how to use the table to find critical values for right-tailed tests. So if the test is right-tailed, use the area under the significance value for these specific degrees of freedom. So let's do some examples. You'll see this is very similar to the other ones that we've done. So our first example says to find the critical chi-square value for 15 degrees of freedom and sigma equals 0.05. Sorry, sigma alpha equals 0.05. So I'm going to open the table. Okay. So this table is pretty straightforward. So it wants us to find the critical value for 15 degrees of freedom. So if I come to the left here, I have 15, and then we have a significance level of 0.05, and that's listed up here, and they intersect at 24.996. So that's your critical value. And remember, this is only a right-tailed test, so it's only positive 24.996. So 24.996. Okay, so why don't you guys try this one? Find the critical chi-square value for 22 degrees of freedom when your significance level is 0.01. So go ahead and do the same thing I just did, but for this situation, and then send me a private chat with your answer. Okay, so I did get some answers. All of them were correct. So we'll do it together though. So we have 22 degrees of freedom and a significance level of 0.01. So if we just come to our chi-square distribution, I said 22 degrees of freedom, so I'll scroll down a little bit. And then we had a significance level of 0.01, and that lines up at 40.289. And that's it. So that one is going to be our critical value. Okay. Then there's a little thing below that says, note for finding p-values from the chi-square table, it uses the same process of trapping the trapping the p-value as we used for t-tests. So if you remember, whenever we would do the p-value for a z-test, that was okay. We were able to find the exact p-value from the chart. But then when we did it for the t-test, we had to find like a range that the p could be between. And you would get like p is less than this or greater than this and less than this number. So you have like a range of values. Same thing here, we'll end up getting the p-value trapped between like two things. And we'll do an example with that. So we'll do one where we do the traditional method and then one where we do the p-value method. All right, so we're just going to do two examples now to finish off how to do this. So we'll keep working with the example that we've been talking about with the arrests. So we'll finish this one off. So given the data on number of arrests for a certain city on 4 different crimes, the table on the first page, is there enough evidence to reject the claim that the number of arrests for each category of crime is the same? Use alpha equals 0.05 and the traditional method. Okay. So first, let's state our hypotheses. So yes, these are a little longer than when we would write other hypotheses like mu equals 0. Like, it's pretty short. This is about a sentence. So if you scroll back up, our null hypothesis is there is no difference in the frequency distribution for each category. And then your alternative is that there is a difference. So let's phrase this with the context of our question or example that we're working with. So the null would be there is no difference in the number of arrests for each type of crime. So what this is saying is that with the expected frequency that we gave and the observed, our null says that there's no difference between these two numbers. So our null says that this is a very good fit. And then our alternative says the opposite, basically, and says there is, there is a difference in the number of arrests for each type of crime. Just following the generic, like the standard hypothesis for each, with just making it a little specific based on our context. So it does say to identify the claim, but that's given in the like wording of the question. So it says, is there enough evidence to reject the claim that the number of arrests for each category of crime is the same? So that would mean that your null is going to be the claim. Because our null says that these number, like the numbers given of the arrests is the same. So that's the claim. Okay, let's do step 2, which is to find the critical values. So we are doing the traditional method. So that means that we find the critical, it says values, it's just value, because this is only a right-tailed test. So we find the critical value from the table. We have the critical region and the non-critical region, and we reject the null based off that. So let's write down the things we need to know to find the critical value. So we need to know our significance level, which is 0.05. And the only other thing we need to know is the degrees of freedom. So the degrees of freedom were defined as one less than the number of categories. And we have 4 categories of types of arrests. So the degrees of freedom is 4 minus 1 or 3. Okay, so using those 2 pieces of information, let's go to our chi-square distribution and find the critical value. So we're working with 3 degrees of freedom and significance of 0.05. That puts us at 7.81. Okay, so 7.815. All right, I'm going to draw the critical region versus non-critical region. And this is going to look slightly different than all the other ones I've drawn, because remember, this is not a normal distribution. This is a chi-square distribution. It only falls on the positive side. It's not symmetric across 0, and it is always skewed to the right. So just keep that in mind. This is not supposed to look like a normal distribution. And I'm going to try my best, but I've only drawn the chi distribution like 3 times in my life. So here we go. Let's see. Okay, not too bad. So it is definitely skewed to the right, and you can see it's only on like the positive side of like what would be like the x-axis here. So this is like 0 here. Okay, so we're going to draw the critical region, and the process for doing this is the same as all the other ones. So you just need to label where this number is. So 7.815, and I'm going to shade this in, and this is my critical region. All right, now we just need to compute the test value. So let's use that formula that I wrote down. So we had chi squared is equal to the sum of O minus E squared over E, where O is the observed value and E is the expected value. So we do this for each possible category. So I'm going to scroll back up to my chart. Okay, so for my first category of theft here, my observed value is 38 and my expected value was 40. So now I just need to plug those things in, and then I'll do this for each one of these categories. Okay, so like I said, in my first one, the observed value was 38. The expected was 40. And then I'm going to square this and put this over the expected one, which was 40. And then I do this for all the other categories and just add them together. So for my second category, my observed was 50 and my expected was 40. So I square that and put it over 40. And I just need to do two more. For my third category of arrests, the observed was 28 and the expected was 40. Square that, put it over 40. And then I'll do the last category where my observed was 44 and my expected was 40. And there we go. And then you can just use your calculator to figure out what all of these things are. So this first one is going to be 2 squared over 40, which gives you 0.1. The next one is going to be 10 squared over 40, which is 2.5. My next one's going to be negative 12 squared over 40, to 3.6. If you're putting these into your calculator, be very careful that you use parentheses on the numerator. If you do not put parentheses there and just throw the squared in, you will not get anything close to accurate. So make sure that you put parentheses where I've written them in the numerator. And then for the last one, it's 4 squared over 40, which is 0.4. And if I add all these together, I get 6.6. That is my test value. Okay, let's put where our test value is on the distribution that I drew. So our test value of 6.6 is probably around here. And that is not in the critical region. So what do we do if the test value is not in the critical region? Do we reject it or do we not reject it? All right, not reject. Yeah, so if our test value is not in the critical region, then we don't get to reject it. So in order to reject the null, our test value has to fall within that critical region. So in this case, we have do not reject the null. Exactly. Okay, and then we just have to summarize these results like usual. So to summarize these, I'm just going to say there is not enough evidence to reject the claim that there is no difference in the number of arrests for each crime, or each type of crime. Okay, and I also put this little chart on here just to like help us understand and visualize maybe why we don't have enough evidence to reject the claim that there's no difference in the number of arrests for each crime. So let's look at this little chart here. I'll zoom in. So the blue points and the blue line represent those observed values. So those blue points here represent the amount or the number in our sample that were observed for each type of crime. So we have the number of thefts, number of property crimes, number of drug use, number of driving under the influence. So this like blue, those blue points, those represent the observed ones. Where the red, like orange stars represent our expected ones. And if you notice, all the stars are at 40 because our expected value was 40 for each. So remember, we are testing how close these frequencies are. So we concluded that there wasn't enough evidence to reject the claim that there's no difference. Or in other words, we said that we could not accept the fact that there, what am I trying to say? Hold on. Let me get my words correctly. Sorry, we didn't have enough evidence to reject the claim that there is no difference here or that they're the same. And that makes sense because like these are like pretty different. Like they're not really close. So by looking at a chart, you can see that these are pretty far. So that might help if you look at like the expected versus observed values on a graph. This is also in the book, so if that helps at all, but they're not super close. It's not terrible, but it's not great. And there's like some charts in the book that tell you, like show you pictures of like a good fit and a bad fit. So it's not good, but it's not like terrible. It's kind of like in the middle. So we don't have enough evidence to reject the claim that there is no difference. So that's just like a visual, I guess, to go along with. Okay, let's do this next example, which is the last one that we're going to do. And this one's going to use the p-value method instead. So I'll read it, and I think I'm going to work through the steps with you guys. So I'll like have you try and do some on your own and like send me your answers as we go. We'll see. So this is a different type of example, one, because it's the p-value method, and two, because this is using that different type of expected value. So instead of taking the total number of observations or the sample size and dividing it by the number of categories, we're going to calculate them using probabilities this time. So our example reads that a researcher read that firearm-related deaths for people aged 1 to 18 years old were distributed as follows. 74% were accidental, 16% were homicides, and 10% were suicides. In her district, there were 68 accidental deaths, 27 homicides, and 5 suicides. So we have these percentages, or like the probability that something is, accidental, homicide, or a suicide. But then we have this sample where this researcher found in her district that 68 were accidental, 27 were homicides, and 5 were suicides. At a significance level of 0.10, test the claim that the percentages are equal. Okay, so let's write down first our null and alternative hypothesis. These are a little longer, like I said, than the usual, but the null is going to look like this. So deaths due to firearms for ages 1 to 18. So remember, our null says that there is no difference. So our null is going to say that the deaths due to firearms are distributed exactly how this researcher read that they were. So our null is going to say that they are distributed as follows, where 74% are accidental, 16 are homicides and 10% are suicides. So our null says that there's no difference, and this is actually the case. This is true. Our alternative is going to say that the distribution is not the same as stated here. So it's going to say there is some form of a difference. So the null is going to say the distribution is not the same as stated in the null. So the null says this is the distribution, this is correct, there is no difference here, and the alternative says there is a difference and it's not the same as stated in the null hypothesis. Okay, let's go ahead and fill out this table here. So let me draw some lines. So we want to put in the observed number of each of these. So the observed one always comes from a sample. So this problem tells you that in this researcher's district, she found these numbers. So this is going to be the observed ones. So this is what she observed herself. So she found that 68 of them were accidental, 27 were homicides, and 5 were suicides. So the observed values always come from a sample. So now we have to do the expected values ourselves. So because this problem gives us some probabilities or percentages, it tells us that 74% of these deaths are accidental. So this is just like something that the researcher read. So she read that 74% are accidental, 16 are homicides, and 10% are suicides. So in order to calculate these expected values, we're going to use the formula E equals N times P, where P is the probability of one of these events. So N is going to be the total number in the sample. So the total number in the sample is going to be 68 plus 27 plus 5, which ends up nicely being 100. And then for each of these categories, we have to do N times the probability of that type of event. So for accidental, we have 100 times the probability of one of these being accidental, which is 74%. So 100 times 0.74, which gives you 74. And then for homicides, we do 100 times the probability of one of them being a homicide, which is 0.16, so 16. And then for suicides, we do 100 times the probability of that, which is given by 0.10, so 10. So now we've filled in here our observed and expected values. You can see the different types of methods here. Where on the last one, we just took N and divided it by the number of categories. And where this one, we specifically took N and multiplied it by the probability of each type of event. So now let's compute our test value, which is given as the sum of O minus E squared over E. I'm going to let you guys try and do this one since I did the last one for you. So try and figure out what the chi-squared value is, and then private chat me your answer when you get it, and we'll go over it together. But try this on your own. I really recommend it because until you try something on your own, you might not realize that you don't understand it. All right, let's go ahead and do this together. So this looks like observed minus expected squared over E for each category. So for our first one, that's going to be 68 minus 74 squared over 74. And then we're going to add to it 27 minus 16 squared over 16. And lastly, 5 minus 10 squared over 10. So if we plug this into our calculator here, we should get 10.549. Okay, so hopefully you got that when you did it, or 10.55 if you rounded. So any questions before I move on to finding the p-value? Okay, so to determine the p-value, this is going to be really similar to how we did with the t-distribution. So to do that, you just need the test value and then the degrees of freedom. So we need to know that the degrees of freedom is going to be the number of categories minus 1. So 3 minus 1 gives us 2. All right, so let's go to our chi-square distribution. So we have 2 degrees of freedom here. And very similarly to the t-distribution, we're going to come across this row here, the one that 2's in, and we're going to find the 2 numbers that our test value is in between. So our test value is 10.549. So if we come along here, these are all pretty small. Once we get to the end, we see that 10.549 is between these 2 values. It's between 9.210 and 9.597. And that tells us that our p-value falls between 0.005 and 0.01. Like I said, you'll get a range, you won't get an exact number, but that will be enough for the problems that I give you. So that tells us that our p-value is between 0.005 and 0.01. All right, so lastly, we just have to decide if we want to reject the null or not. So if you remember, to reject the null, our p-value needs to be less than the significance level. So let's see if that's true. So p is between 0.005 and 0.01. Our significance level that we have is 0.10. So no matter what p is within this range, this is always less than 0.10. Because at the most, p is barely less than 0.01. And 0.01 is always less than 0.10. So that means that indeed p is less than our significance level, which means that we get to reject the null. Yay! And lastly, we just need to summarize the results. So we say there is enough evidence to reject the claim that, and remember our claim was that the distribution was 74% accidental, 16% homicides, 10% suicides. So we have enough to reject the claim that the distribution is 74% accidental, 16% homicides, and 10% suicides. right, anyone have any questions on this example? All right, so I'm gonna stop